So just the existence of solids and liquids is due to intermolecular forces, but some other properties also arise from intermolecular forces. And these include surface tension, which the astronaut was talking about, viscosity, and capillary action. So we'll talk about surface tension first. This is a picture of a paperclip floating on water. Do paperclips float on water? They shouldn't, right? Paperclips are made out of metal, and they are more dense than water. Needles shouldn't float on water either, and yet if you have pure water and a very clean paperclip or needle, you can get it to float on the water. Do you see how the surface of the water is depressed here? It's almost like there was a blanket or something, a skin on top of the water, and the paperclip's kind of pushing into it, but it can't go all the way through. That is due to surface tension. The reason that droplets of water on this spider web form little tiny spheres is also due to surface tension. Surface tension is the tendency of liquids to minimize their surface area. And of course, it can be measured. It can be measured as the energy needed to increase the surface area by a specific unit. Mm-hmm.
That's a boat split, though, isn't it? Because they have more surface area, like, you know.
Boats float due to displacement.
Displacement, okay.
Yeah. So boats also are more dense than water and yet float. But that's because of the shape of the boat, which is really going more into physics than I feel comfortable going into.
Okay.
Yeah, but it's not surface tension. But surface tension is the reason those little water skater bugs can skate around on top of the water. If you look at them closely, their little feet are making kind of indentations in the water. So this is a picture of a trout fly, and this has a metal hook inside of it, and then it's got feathers and stuff tied on there. And you can throw this out on the water, and it will float on the water, even though it's more dense than the water. Because in order for this to sink, it has to increase the surface area of the water, and the surface tension doesn't want to do that. That requires a certain amount of energy. And the fly is not heavy enough to create more surface area. So how does this work? Here we've got a two-dimensional illustration of a liquid. So here in the middle, any given particle is surrounded and interacting with 6 different neighbors. Whereas on the surface, these molecules are only interacting with 4 neighbors because there's nothing on this other side. So these interactions stabilize the molecules. Remember, when we're talking about potential energy, it's like we're looking at altitude below sea level, right? So sea level is the surface of the ocean, and as you go lower in altitude, you've got negative altitude, right? You're going negative. So if you think about an atom or molecule that's not interacting with anything, you could say, well, we could call that 0, right? When it interacts with something, it lowers its potential energy, and so it becomes more stable. So this guy in the middle is more stable, lower in potential energy than this guy is, right? So in order to increase the surface area, we need to have more molecules become surface molecules, and that's going to require us to increase the potential energy of the substance. It doesn't want to do that.
And how do you increase potential energy?
So
By math?
this has a higher potential energy than this guy. We can also talk about this, the idea of a ball rolling down a hill, right? The ball's going to roll down the hill, down towards the lowest point, right? These are going to go to the lowest energy that they can get to. This one is lower energy than that one. This one would like to go to this one to be lower in energy. This one is not going to roll back up the hill and become like this, because that's higher in energy. So if you want to break the surface of the water, if you want to increase the surface of the water, then you have to put energy into it. And so a sphere is the shape where you have the smallest surface area relative to its volume. So the minimum surface area. If the intermolecular forces are weaker, then the surface tension decreases. Then it's easier to break into that water the liquid to increase its surface area. And so this is why water forms spherical droplets, because that's the geometric shape with the smallest surface area. This is a picture from that, this is the same guy that we saw in the video, Canadian astronaut on the space station. And so here he has a really, really big drop of water. But it's spherical. We don't see drops of water that big on Earth because they get distorted by gravity, because gravity's pulling on them, okay? And if you think back to, we're going to do this in class today as well, if you think to pipetting or burette, using a burette, and you got this drop hanging, right? It's not going to be a perfect sphere, is it? It's going to get distorted. Once it breaks, then it will jiggle around, and at some point it will become a perfect sphere. I should probably find some of those really fast videos on YouTube where they look at the droplets of water, how they change after they get shot off of things. But this is possible in space because there's no gravity. Viscosity is another effect of intermolecular forces, and viscosity is the resistance of a liquid to flow. That also can be measured. Viscosity is greater in substances that have stronger intermolecular forces. So in order for a liquid to flow, the molecules need to slide past each other, right? And so if it's Velcro, they're really sticky and it's hard to pour, like honey. Honey is a liquid, but it's really thick and it pours like so slowly, right? Whereas water is not as viscous and it pours more easily. There are compounds that are even less viscous than water, things like gasoline, which pour more easily, but we don't really have that much experience looking at liquid gasoline. It's kind of dangerous. So the viscosity is going to depend on the strength of the intermolecular forces, and it's also going to depend on the molecular shape. We talked about the dispersion forces and how those can depend on molecular shape. When we have longer molecules, then they can have more surface area to interact with each other, and they'll stick together better. They can also literally become tangled with each other. So here we see this is a trend of increasing viscosity as these hydrocarbons get longer and longer. These are not linear molecules like a piece of uncooked spaghetti, just straight and always straight. They're more like cooked spaghetti. They're flexible and they can twist around. And so the longer these get, the more twisted up they can become and the more viscous they are. Viscosity also depends on temperature, because if you increase the kinetic energy of those particles, then they can move past each other more easily. What happens if you heat up honey? Have you ever done that? It gets thinner, it gets runny, right? It becomes less viscous. Or maybe pancake syrup and somebody stuck it in the fridge. And you pull it out and you're like, oh man, just like pours so slowly. Like molasses. Yeah, molasses is also very viscous. I could tell you a story about molasses. So at a lower temperature, things are going to be more viscous, and a higher temperature, they'll be less viscous. So one place that viscosity is very important in everyday life is in motor oil. So the engine in your car needs lubrication so that the parts don't get super, super hot as they're moving against each other. And the motor oil needs to be viscous enough that it will stay up on the parts that are moving without, instead of like water where it will just fall to the bottom in the oil pan. But you don't want it to be too viscous, because then it'll be kind of sticky and actually gum up the parts. So you need just the right viscosity for your motor oil. At low temperatures, oil becomes more viscous, and at high temperatures, it becomes less viscous. So places like Minnesota, where they sometimes have negative 40 degrees Fahrenheit, absolute temperature, not wind chill, well, the motor oil that you used in the summer when it was 95 is probably not going to work so well at minus 40. Yeah.
Does that apply to every, or just like?
All viscosity always decreases with increasing temperature. Yeah. Mm-hmm.
Is like tar, is that just a very viscous liquid, like, or is it?
Yeah. So there are some substances like tar and even like glass that we think of as being solid, and yet it's kind of questionable whether even at room temperature, you've maybe heard about glass from really, really old houses that's thicker at the bottom than it is at the top from the windows, because it's just been standing vertically for like 200 years. They didn't make it that way. What happened? Well, in a sense, glass is a liquid, an extremely viscous liquid. And very slowly it's sinking down to the bottom. And so if you think about tar, if you heat tar up, right, it will melt and become a liquid. And the hotter it gets, the less viscous it gets. And as it cools down, then it becomes more and more viscous and eventually becoming at least a semi-solid.
Is it like the same thing with asphalt then? 'Cause I know that like that kind of gets looser as it heats up.
Yeah, it with asphalt. I mean, you've probably seen. I live in Reedley, where there's just a lot of semi trucks hauling fruit, and some of the stop signs, the asphalt is just kind of all like buckled up in the summer because it gets really hot in the sun. And then these trucks are stopping on it, and they just make a mess out of the roads. But then you kind of have to. Well, is it actually a liquid, or is it just melting a little bit? So some things will melt sharply, and other things will melt slowly. They'll just soften. Like if you think about chocolate, right? Chocolate doesn't just go from a solid to a liquid. It kind of has a transition, right? Whereas when ice melts, the liquid water, behaves like liquid water, right? You don't really have soft ice before it melts. So some of those are substances that just soften before they actually melt. Yeah. One of the really cool things about modern motor oils, you can get all synthetic or semi-synthetic. These have special polymers in them that control the viscosity of the motor oil and combat the changes from temperature. So they have polymers in there. At low temperatures, those polymers coil up and make little spherical molecules, so they're not able to be attracted to each other, and so that minimizes the increase in viscosity when the temperature goes down, because the molecules are changing shape. And so now the viscosity isn't changing very much. And then when you heat that motor oil up, they uncoil and they get long and tangly, and they're going to mitigate the decrease in viscosity due to an increase in temperature. So very, very neat application. Any questions? Capillary action is another result of intermolecular forces, and this is the ability of a liquid to flow against gravity up a narrow tube. So I hope nobody's squeamish, but so this person's having a finger prick, and they're just taking a little sample of blood. So this is a little tiny capillary tube. It's open at this end, and you touch it to the blood, and the blood just runs up the tube. You don't need a pipette bulb or something to suck it up in there. It just runs up there all by itself. That's capillary action. Here we have a bunch of tubes of different inside diameters, and we see that the really, really skinny one, the liquid goes all the way up here, whereas the fatter ones, it does not go up as far. So what's causing the liquid to go up like that? is capillary action, which is a combination of two different forces. There are cohesive forces. The molecules within the liquid are attracted to each other. And there are adhesive forces, which is the attraction between the liquid and the surface of the tube. So you can see on these that the liquid is a little bit higher at the edges. It's kind of creeping up the edge because it's attracted to the glass wall. And as it creeps up, it's going to, by cohesive forces, pull its neighbors up behind it. It will go up to a point, and then it'll stop, and that'll be due to gravity. So if the tube is wider, it will not be able to go up as high, and the more narrow tube can go higher before gravity stops it. And capillary action is the reason that we see a meniscus on the surface of a liquid. So here's a test tube with water in it, and there's that meniscus. And we learned that when we're looking at graduated cylinders and stuff, we're supposed to measure the bottom of the meniscus, right? Why does the water curve like that? Well, adhesive forces are pulling the water at the edges up, and cohesive forces are keeping most of it here. So we're pulling some of it up, and then we get this curved shape. And that depends on how strong the intermolecular forces are. If you have something with weak intermolecular forces, you're going to see less curvature or maybe even a flat surface and no meniscus. This is mercury. Mercury's meniscus is upside down. So it actually curves up in the middle because mercury is not attracted to the glass walls, and the the cohesive forces are stronger, and so it's trying to stay together and avoid the glass, and so it's making this bulge in the middle.